Before we begin and introduce today's speaker, Professor Andrew Rappe, let me briefly share a bit of background about the One Horn Lecture Series. The One Horn Lecture Series has been a proud tradition of this department since 1974, and it has been essentially established to honor Kent Van Horn, who is a distinguished physical metallurgist and a remarkable figure in the field of material science. And Van Horn name is very familiar to many of us around the campus, and it's also for a good reason. Kent Van Horn graduated from this university in 1926 before going to Heidelberg to do his PhD in Germany, and later started his professional career in Alcoa and came to a small town near Pittsburgh called New Kensington, and eventually become the corporate vice president of Alcoa. Kent's father, Frank Van Horn, is the founding father of what we know as the Material Science and Engineering Department. And he was a geologist and mineralogist and known for his love of collecting rocks, his extensive trips, as well as his love of sports. And many of you, in fact, know we have the Van Horn Field next to our building here in front of the Wheel Center, named after him. And so his legacy can be seen all over the campus. And he's credited also for establishing the first successful football team at the university. The Van Horn family connection to our department continues to this day. Carl Van Horn, Kent's son, continues to maintain close ties with us. And although Carl began his career as an engineer, later he transitioned to finance, but he still remains a dedicated supporter of our department and this lectureship. The Van Horn Endowment funds this annual lectureship series, which brings to our campus an eminent scholar, a scholar in the field of material science and engineering. Our faculty essentially carefully selects a leader in the field to deliver this series of lectures. A central goal of Van Horn Lectures is to engage our students and providing them an opportunity to interact directly with a leader in the field and discuss their research through group meetings and informal conversations. These exchanges provide our students valuable insights and expert perspectives that enrich their own academic and research experiences. This year, we are delighted to welcome Professor Andrew Rappe as our 2025 Van Horn lecturer. And I would like to, at this point, introduce him as our speaker for 2025. And Professor Rappe is the Blanchard Professor of Chemistry and Professor of Material Science and Engineering at the University of Pennsylvania. He earned his BA in Chemistry and Physics, summa cum laude from Harvard University in 1986, PhD in Physics and Chemistry from MIT in 1992. And during his PhD, he was recognized both as ONR Graduate Fellowship with ONR Graduate Fellowship and JSAP Graduate Fellowship. He went on to serve as an IBM postdoctoral fellow at the University of California, Berkeley, before joining the faculty of Penn. Over the course of his career, Professor Rappe received numerous prestigious awards, including NSF Career Award, Alfred P. Sloan Research Fellowship, and Camel Dreyfus Teacher Scholar Award. In 2006, he was named a Fellow of the American Physics Society, which is a testament to his pioneering contributions to materials theory and computational chemistry. Professor Rappe's international reputation is equally distinguished. He has served as the Western Visiting Professor at the Weizmann Institute of Science in Israel, Ziqiang Professor at Shanghai University, and a recipient of both the Humboldt Research Award in Germany and the Cheney Fellowship at the University of Leeds. While you will hear a lot about his cutting-edge research and scientific impact during the follow-up introductions in the second and third lectures. I would like to focus another dimension of Professor Rappe's work, and that is his remarkable dedication to teaching and mentoring. He is one of the founding co-directors of Vangelos Integrated Program in Energy Research, known as HOIP, which is an honors program at Penn designed to train the next generation of sustainable energy leaders. And they build a unique structure where you can earn a BA and BSc at the same time, essentially immersing the students in an interdisciplinary research at the interface of science and engineering. And this reflects Professor Rappe's long-standing commitment to breaking boundaries between disciplines and applying science for the benefit of society. What stands out most about Professor Rappe is his genuine investment in students and colleagues. Even after arriving to Cleveland yesterday, he spent over 3 hours over Zoom with his students giving lectures and office hours before joining us in the reception. And this, I think, is a good example of his enthusiasm and generosity that define his approach to mentorship. And on a personal note, I had the privilege of collaborating with him on several proposals, and our discussions, and mostly his questions, many times challenged me to rethink my experimental strategies and broadened my, essentially, perspective. And for that, I remain deeply grateful both for his guidance and friendship over the years. So without further delay, please join me welcoming Professor Rappe, who will present the first lecture of the 2025 Van Horn series titled Hybrid Perovskites as a Novel Platform for Optoelectronics.
Well, thank you, everyone. It's really a great honor to be here and to become part of this wonderful tradition of honoring the Van Horn family and their contributions to Case Western Reserve University. It's great to be back at Case Western Reserve. I fondly remember the first time I was hosted by Walter, and then I was hosted more recently by Alp. And I have many friends here in the department, and I like to think that I'm in the process of making some new friends. Thank you for your generosity in sharing your research contributions with me all during the day, and I look forward to an engaging week together. I will tell you that I got my start in material science fairly early. It was in 5th grade that I did a project on crystals. And so in construction paper, I cut out squares and rectangles and rhombuses, and I taped them together to show my 5th grade colleagues what the differences were between cubic, tetragonal, orthorhombic, monoclinic structures were. And the capper of the presentation was supposed to be that I would bring in a supersaturated solution of sodium acetate, and we would show it crystallize. So my mother brought the solution to school, drove it all the way there, and walking in the door, it crystallized before we got there. So the teacher found a hot plate, we re-dissolved it, and all was well. And back then we had something called an overhead projector. Probably most of you don't know what those are. But we put a little bit of solution in a petri dish on the overhead projector. So as the crystallites grew, they were humongous up on the screen. It was quite a show, I think. So I think that may have been my high point in material science. But let us continue on. Okay, so today I'm going to tell you some insights into a very unusual, flexible, designable class of materials known as hybrid halide perovskites. I think that's not really a theme, it's more of a topic. And so I was thinking, what is my theme? But then last night, one of you told me that a big push here at Case Western Reserve is mechanical testing. And I realized all the projects I'm going to tell you about in one way or another involve, if we deform this material, how do its properties change? How do its mechanical properties change? How do its chemical properties change? How do its optical properties change? It's so interconnected that you can think of this presentation as an exploration of mechanical testing in the wonderful world of hybrid halide perovskites. And that's in fact why I changed the title to An Unstable Platform for Stable Optoelectronics. So let's have some fun. So I'm really going to tell you 3 different stories. The first is looking at structural and mechanical properties of hybrid perovskites and how they relate to their optoelectronics, and then tailoring lattice dynamics and how that affects the optical and electronic properties, and then finally tailoring interfaces and surfaces. Okay, so I actually imagine in this department most of you know what I'm talking about when I say perovskite, when I say halide perovskite, and even when I say hybrid halide perovskite. But to introduce briefly, this is our friend, the cubic perovskite structure. So we have corner sharing octahedra with the cation in the center, and then halide ions on the corners. And then in the center of 8 cages, we have another larger cation. And the amazing thing is that if you pick a metal such as lead, it's large enough, these octahedra become large enough, you can actually hide a small molecule in this cube octahedral site. And that is what we call a hybrid perovskite. It's part molecular, part inorganic. And the exciting thing is they have shown great promise for converting sunlight to electrical energy. And this is a congested chart, but I'm hoping you are familiar with what this is. The idea is that NREL is the gatekeeper for certifying solar cell performance. And so these are the years on the x-axis, and this is the cell efficiency. And what you can see is that lots of technologies started and then made very slow progress. So the slope of their lines is almost flat, the blue, you see, the purple. But now look at the red circles with the yellow inside. This is the hybrid perovskite world. The progress is extremely rapid. The slope versus time is better than any competing technology, leading to cells that are as productive, as efficient as silicon solar cells. So that's a remarkable accomplishment. They're not yet inserted in the market to a great degree, and there are various reasons for that which we could discuss. But from a scientific point of view, they're very promising, and examining how to integrate them into the market is a current ongoing applied research initiative. Okay, so what's really happening? Sort of the story is that actually the earliest papers on hybrid perovskites, I think, go back more than 100 years if you look closely enough. These were not discovered recently, but they've kind of been rediscovered over time. And they were studied for various applications. But recently, they had a rebirth of interest because they were incorporated as an additional component into dye-sensitized solar cells. And they've also been looked at as an additional layer onto silicon solar cells. But then people eventually realized that they could serve as the main solar absorber material. And that brings us to the record efficiency that we're seeing recently. There are a variety of interesting potential applications, everything from catalysis to sensors of various kinds. But what you'll hear about is that there are significant stability issues. And so that can involve stability, thermal stability, chemical stability, stability against moisture, stability against aging. And so understanding the properties of these materials and evolving them from a scientific project to an actual product that can be used is a continuing challenge. So one theme of my remarks will be a clever development over the last decade or so is to move from the 3-dimensional cubic perovskite structure to layered or 2-dimensional perovskite structures, where you have a certain number of layers that definitely look perovskite-like, but then there's a large molecular spacer layer in between, and then the crystal repeats. It turns out that by making this kind of hybrid structure, there's so much more hydrophobic molecular species, that these seem to have much better stability. And so it's a promising new direction to find a sweet spot of favorable optoelectronics and beneficial stability. So this is just kind of a simple paradigm for you to start to think about how these materials are assembled. You imagine you have the reagents to make the hybrid perovskites, so such as lead ions and methylammonium, these small A cations. But then you say, what should I put for my spacer layer? It turns out that materials with at least one benzene ring are much more hydrophobic or seem to promote stability better than the pure alkyl ones. So we'll say there's a benzene in there. But look at this. If you take just a benzene ring with two ammonium groups, it turns out this doesn't form a layered 2D perovskite. If you then put one, I don't know if you know this notation, this means there's one additional carbon here with two hydrogens, so it's a little bit longer molecule. This one will form, but it turns out not to be stable. But amazingly, if you just extend further with two carbons on each side, spacing the ammoniums away from the benzene ring, it'll form and it turns out to be stable. So this just gives you a glimpse that there are many parameters for materials design that are opened up by this complex set of materials. Okay, so let me begin by talking about true mechanical testing. What happens when you compress and expand these materials? It turns out they're fairly mechanically soft, and we actually view that as mostly a good thing. So I was mentioning silicon cells are kind of the incumbent technology for solar, but imagine if you had a soft material. You could imagine depositing it onto a flexible film and having a certain amount of photovoltaic capacity with you in convenient form factors that you could roll up or even incorporate into clothing. You know, people dream various dreams. And so understanding the softness of these materials and how to preserve them and benefit from them is important. And so I had a wonderful chance to collaborate with Lin Lu, who is an amazing experimentalist examining mechanical properties of these 2D hybrid perovskites. So to try to understand the mechanical properties, we look at a family of materials. Sometimes you can't learn so much from each individual, but you can see patterns. So you can see here there's one layer of octahedra, and then you have those molecular spacers, then one layer of octahedra. So we're going to call this n equals 1. Then we go back, there's 2 layers, and then the spacer, and then 2 layers, then 3, 4. And then n equals infinity will mean, we never get to the molecular spacer. This is back to the 3D hybrid perovskite. We would say that's the n equals infinity member of this series. Okay, one thing to note is, do you see the part where it's like the perovskite layers? There are the small molecular cations are embedded here, except for n equals 1, where there's no pockets. You get this small molecular cation as soon as you get to n equals 2. That'll crop up later. So there's 2 kinds of tests that we like to do. One is to take the hybrid perovskite material and exfoliate it so it's thin, put it on a stretched rubber sheet, and then let the sheet contract, and note at what point you get a wrinkling instability, and this can give you a measure of the in-plane Young's modulus. And the other thing that's important to do is nano indentation, where you can take note of the relationship between the force applied to the tip and the amount of penetration into the material, and that gives you a readout on the out-of-plane elastic modulus. Okay, so when you do this sort of nano indentation, you can start with the tip at the surface and then embed it, and you'll increase the load, and you'll go to a greater depth, and then you could start to take the load away, and the tip will come back out. And so there are 2 different ways that people can yield elastic moduli from this. One is to look at the curvature right when you're entering the material, and that's referred to as the Hertzian regime. You can see here fitting this to like a parabola. And then taking the slope of the unloading regime, you can get an elastic modulus as well, and this is referred to as the Oliver Farr approach. And so I'll say more about this as we go, but basically we feel that you can see here that the material is quadratic for a while, and then there are these jagged regions. These are referred to as pop-ins. We think there are various defects that are created. We can call this a single crystal if we like, but it's such a soft material. There's lots of like sliding defects and voids. And so as you compress, you're kind of actually improving the crystallinity as you go. And so we think that the unloading part of the mechanical testing curve is more representative of the intrinsic properties of the material. Okay. So now what can we do from the point of view of theory? We can calculate all the elastic moduli using quantum mechanical calculations, and then we can use the elastic moduli to get the Young's modulus, and we can go in the Voigt limit of continuous strain or the Royce limit of continuous stress, and so we can then plot our theoretical results as blue and red dots. And we can compare to the Oliver Farr results that we think are more representative of the idealized crystalline material, and those are shown as green X's on this plot. And what you can see is that the plot of the experiment is quite parallel to the plot of the Royce results, except we sort of need to use the Voigt result for n equals 1. And our analysis tells us that the n equals 1 result is actually quite different from all the others. Do you remember that n equals 1 doesn't have the little molecule in between, and so there's some shearing behavior that's possible in the n greater than 1 that's not possible with n equals 1. And so the continuous strain limit is more appropriate for n equals 1, whereas we use the Royce limit for the rest. And so we're quite happy with this level of agreement, but then we realized that these simulations are at t equals 0. And there's well known in the literature how to correct elastic moduli from 0 temperature to make a finite temperature correction. And so when we apply that correction, we go from the gray line that we calculated from DFT, you can have this more or less rigid shift. And so the results agree rather well with the experiment. But they're a little bit of an underestimate. Okay. So the final thing that actually helped us quantitatively model the elasticity is to re-examine the molecular layers. Remember our friends, the molecular layers. There's a benzene ring here, but it's tilted, so you're only looking at it side on. Here, you can see the molecule a little bit better over here. So this was the way we modeled it. This is actually a smaller unit cell, so it's sort of the first thing you would do, where you have the molecule stacked up like this. We'll call this parallel pi-pi stacking. But it turns out some of the molecules can swivel around relative to the others, and that T-shaped pi-pi is actually a little bit lower energy. And in fact, that drops the elastic modulus right into the region that is where it's experimentally measured. And so we think that the molecules can swivel around, become a little bit more stable, and this increases the elastic modulus slightly because they have this stronger interaction. So that kind of gives you a view of how we can model the soft material behavior of two-dimensional hybrid perovskites, which I think are a promising material for future solar applications, as well as light harvesting, including photocatalysts and sensors. Okay. Now, I was saying at the outset, we can look at how this material behaves, but then we can say, how can we change the material to give it more favorable properties? So I'd like to talk about another really joyous study working with my friends here, including Mercuri Kanatsidis and Ted Sargent. In my group, this was led by Aaron Schenkler. So we call it 2 spacers, 1 perovskite. Okay, so this is going to seem a little crazy, but my talented experimental friends were actually able to get this to work. Okay, so we're still talking about these 2D hybrid perovskites. So you see here, you have the perovskite layer, another perovskite layer. Now you say, how do the molecules arrange themselves? If you only have one ammonium, and then you have some organic stuff, and then you have an ammonium and you have some organic stuff, what's going to happen is, can you see that the peaks of this octahedron align with the equatorial halide of this one, and the peaks of this one align with, they're shifted by half a unit cell. Can you see that? So we have two molecules, and that causes them to shift by half a unit cell. This whole configuration goes by the name Ruddleston-Popper phase, okay? So just for my curiosity, how many of you heard of that before this second? Oh, not bad. Okay, very good. So there's another thing that's called Dion-Jacobson phase, where you have one molecule that has two ammoniums. And so it can fit into the trough and the trough. And so that preserves the, alignment you might expect. And so these two are sort of competing things. And it turns out that the DJ perovskites have lower band gaps and have more favorable optoelectronic properties. But for a lot of the large A cations, you wind up with this Ruddleston-Popper phase. So, okay, so can we get the benefits of both Ruddleston-Popper and Dion-Jacobson? Okay, so this is an example. You see, this is just using butyl ammonium. So there's 4 carbons here and an ammonium group, and this is the Ruddleston-Popper phase. And then this one is this molecule called 3-AMP. It has a nitrogen there and a nitrogen there. So it fills the whole thing and makes a Dion-Jacobson phase. So amazingly, if you provide to the reactive system both of these molecules, you get a halide hybrid perovskite with a perovskite layer and then the 3-AMP, and another perovskite layer and then the butyl ammonium. And then it repeats, perovskite in this guy, perovskite in this guy. So it actually makes a 2-material sandwich. Okay, so that's cool. And so we wanted to analyze that. So when we do the calculations, it turns out that the mixing energy is slightly positive. So from a DFT point of view, we would say, no, they would actually like to separate, except that's at 0 temperature. And we think there's an entropy of mixing that's just large enough. And if you orchestrate the kinetics of the reaction conditions, yes, they can get it to form. And they have good evidence that it forms, but we would say it's sort of marginally stable. Okay, and so now what are the structural properties? So we could look, if you look at these octahedra, we're always asking questions about how much do the octahedra tilt. So this angle is very representative of that parameter. And so if you make it only with butyl ammonium, you get a much smaller angle. They're very tilted octahedra. And then if you do it only with the 3-AMP, they're much less tilted. They're closer to 180, which would be untilted. And it turns out that when you have both spacers, the angle is very close to the Dion-Jacobson. So we might hope that we're getting the favorable optoelectronics of the Dion-Jacobson end member. And then we calculated the absorption properties. And so this is what is measured, that if you have the 3-AMP material, and then you have the butyl ammonium, these are their absorptions and these are their corresponding band gaps. And the material with 2 spacers is kind of in between. And so our theory actually reproduces that quite remarkably well. So this just gives you a glimpse of a lot of activity that's going on using organic materials design to create new 2D hybrid perovskites. And I can tell you that in work that's not really completed enough for me to tell you about today, we are doing a broad, sort of thousands to millions of organic molecule search to come up with new ideas for spacer cations and small a cations that would further tune the optical absorption, the carrier lifetime, and preserve properties based on this pioneering study and some of the other physical principles that I'll talk about in the rest of the time. Okay, so now I want to go to smaller mechanical deformations. How do vibrations in the crystal relate to the optical properties? Okay, this is something that we've been studying for a while. So I'm going to tell you about some of our older work in this area and then move to some of our newest work. So I think many of you are familiar with Raman spectroscopy. Raman is a great non-destructive way to probe the properties of materials. So you expect to see the vibrational modes that are Raman active. And if you look at, this is for a three-dimensional hybrid perovskite, but I would make the same point about the 2D ones. If you look at low temperature, look, you see a series of peaks. You would say, ah, good, no problem, a Raman spectrum. But now look, as you go up toward room temperature, you get a very broad, weird double peak. And then look at room temperature. What the heck is this? Do you see? You get response at every frequency. Okay? So that is frustrating. And people would say, oh, that's because of the disorder of the molecule. It's not. We did the same thing with cesium lead iodide, where it's not a molecule, it's just an atom. And you get this same diffuse, almost structureless blob. So that was extremely interesting to us. And we were able to take a first principles calculation. So we're using quantum mechanics and saying, what are the forces on all the atoms? What are all the vibrations? But here's the key. We didn't just calculate the phonons. I'm sure you're familiar with the idea that you can do a Taylor series of the energy and calculate the vibrational modes. We didn't just do that. What we did was we said, let's do a real molecular dynamics study. Molecular dynamics isn't limited to a quadratic approximation. It visits all the structures that the material might actually visit. And then we do what's called a polarizability autocorrelation function. And this is a way to get the real Raman spectrum, not just from the harmonic modes, but from everything. Okay, and when we do that, look at what we get. Do you see? Remember, we had this featureless blob. I would say the red that we get is pretty close to a featureless blob. When we go back to low temperature, we get modes where they get modes. And then we get weird double peak where they get a weird double peak. And then we get this interesting featureless blob. So it actually can be captured in the theory. And so then we can set about saying, okay, now what's going on? Because we have a glimpse into what every atom is doing at every moment in time. So this is our technique. Hopefully this isn't too much math for you. The idea is we take the trajectory. This is what are the positions of all the ions at any given time. Then we Fourier transform that. Then we say, only keep frequencies in a very narrow range. And then Fourier transform back so that it makes a trajectory, but it's only showing what's happening at one particular frequency. So we get movies that look like this. So you can see one particular behavior, but it's not really a phonon mode, because we could look at any frequency in that featureless blob and we can ask, what is it doing? And so it turns out it's doing a complex combination of things. It's doing lead I6 rotations, lead I6 distortions, and lead I6 stretches. It's all the octahedra at these low frequencies. So then we can decompose and diagnose. And at the lowest temperatures, look, it's a lot of distortion, it's a little bit of stretching, and it's a little bit of rotation. But then as you go through the first phase transition to the tetragonal phase, you start to get octahedral rotations around two axes, as illustrated here. And so now for the low frequency part, which turns out to be the most important for the photovoltaic properties, rotation and distortion become competitive. Can you see that? The blue and the orange are almost the same. Then what we get when we get to the highest temperatures, or even room temperature, rotation dominates. Okay, so these octahedra are rotating kind of wildly. And to kind of see that in maybe a way that's a little more familiar to you, if we just do molecular dynamics and we say, hey, how much are you rotating around all three axes? We would say a little, maybe a little. Then you heat up, these guys go a lot more, these don't really change that much. It's mostly around these two axes, but then when you go cubic, it rotates around all three axes equally. Okay, so now I want to tell you sort of the message of what's happening with all this dynamical motion. What I want you to think about is these hybrid perovskites. If you do X-ray diffraction, you'll say, yep, it's a cubic crystal, looks normal to me. But if you look on a picosecond by picosecond, or even maybe 100 picoseconds, different parts of the material are doing very different things. So how can we start to analyze that? Because when you look at a time-independent measurement like X-ray, it's all hidden. So what we do is we try to model how the electronic structure is changing. If these rotations are going wild and distortions are happening, how does that affect the properties that we care about, like what's happening to excited electrons and holes when this thing is acting as a photovoltaic? So we make what's called a tight binding model, where we have excitations happening, and we calculate the energy of putting an electron on any given site and the energy to move an electron from any site to another. Okay, so we developed this tight binding model, and what you can see here is we have the tight binding model, and it fits the bands near the band gap very well. So it's a good enough, simple model for what we want to do. And all that's contained in the tight binding, remember when we did the quantum mechanics, we included every electron, every orbital. All we included are the most important ones. We included the lead S and P and the iodine P, because for the bonding near the band gap, that's all that matters. So we have this lead p orbital. How easy is it for it to send an electron from here to there? That's the hopping. What's the energy of being on the lead? Okay, so now we can connect these distortions to electronic properties. Okay, so we have this picture of a super dynamic world. Everything is migrating wildly, and here, what's the energy of an electron being on a particular site? Or actually, this is the energy for an electron to hop from one site to another. It varies by 100%. Do you see sometimes it's below 1 and sometimes it's above 2.5? And so that's on a very short time scale. So think about an electron trying to move through the material, right? If it's a photovoltaic, the hopping is how the electron gets from here to there, and you get a useful electron. Sometimes it's easy to move, sometimes it's hard to move, and that's fluctuating back and forth on a very fast time scale. So the electrons are dramatically scattered, that if they can't go this way, they go another way. If they can't go this way, they go another way. So you should have a picture that the electrons are not just having a smooth time of it getting through the material. That's what that's telling you. And then the on-site energies. This is just the energy of residing on a lead. Sometimes it's high, sometimes it's low. You can see the blue parts are also wildly fluctuating. So what this means is sometimes the electron's happy over here and the hole is happy over there. Then they scatter. And sometimes you scatter this way, sometimes you scatter that way. But the electron and the hole will never be happy at the same place at the same time. So the electrons and holes are dramatically scattered, but always away from each other, you see? So this dramatic ion motion leads to a very long carrier lifetime. They were always scattering the electrons and holes away from each other. Okay, and we...
Explain the reason for that again. I understood that. What's the physical reason for the electrons and the holes to become separate?
Yes.
We don't have a band gap that's clearly
We do have a band gap that's clearly defined. Oh yeah, this thing's always a semiconductor. It doesn't fluctuate so much that it becomes metallic. So when I was talking about conductivity, it's photoconductivity. If you're already excited, you can move. It's not thermal conductivity like a metal. Yeah, so that's one thing. But here's the idea. Suppose some of the ions move together. That would be a great place for an electron to go and a bad place for a hole to go. Somewhere else, the ions all move apart. That would be a great place for a hole to go. Those are never the same place. There's never a place that says, I want electrons and holes. So they're always scattered to different parts of the crystal. Yeah, so that's what I was trying to convey. Okay, so what we do is we have this tight binding model. We actually solve a one electron Schrodinger equation. We say, how fast will an electron spread out? If it's initially here, how fast will it go somewhere else? And we're actually able to calculate the mobility and the temperature dependence of the mobility, and this agrees with experiment. And so this was the first time that this was done, and it's based on this model of including the distortions in this floppy, soft, hybrid perovskite lattice, and understanding why and how that makes it good for photovoltaic applications. So now the next thing is, if we say, oh, all these ion motions are very interesting, how about if we, as the experimenters and theorists, drive vibrational motion? So in this project, my friends excited one of the vibrational modes on the molecule in the hybrid perovskite to see the results. Okay, so I'll tell you about that. So this is their experimental apparatus. They send in, here. Are you familiar with this kind of a chart? This would be like the ground state of the system, and then you could excite a vibration. That's what this red line is. This is just exciting vibration, but then you could go to excite an electron using visible lights. This is infrared light and visible light. But now, if you have IR excitation first, this blue line will be enough so that you can reach the excited state. So we would say in laser language, we detune the visible excitation. So if you don't have the right vibration in the right place, you can't get any excited electrons. But if these can talk to each other, then yes, you can. So we call this vibrationally promoted electronic resonance, which is an acronym VIPER. Okay. So they use a broad pulse because it's going to be ultra fast, but the only thing it excites is this one mode on the molecule in the hybrid perovskite. Here, this is the molecule we happen to be using. It's called 4-mamidinium, and the mode we're exciting is the carbon zigzagging back and forth between the two nitrogens. And here is their signal. If you don't do the IR pulse first, then you don't get a long-lived response in the VIPER signal. And if you have IR first, then only when you excite around 1700 do you get a long-lived vibrationally promoted excitation response. Okay, so what I want to show you, basically, we asked why are these vibrations helping to excite electrons over the band gap? And so the vibrational lifetime is actually 1.8 picoseconds, which is very slow. The signal that they see decays in 300 femtoseconds. So we said, if you excite the vibration and it's still going for 1.8 picoseconds, why don't you keep having excitations? It turns out the crucial thing, remember, the molecule has the vibration, but the excited electron is on the backbone, the lead halide backbone. So how do those two things talk to each other? Through the gentlest of bonds, a hydrogen bond. And so what we're able to show is that if you have cation motion, so it's still vibrating, but if this guy rotates and breaks a hydrogen bond, then you lose the connection and the VIPER signal goes away. So we actually did a molecular dynamics study of this material, and we were able to just keep track of all the hydrogen-bromine distances. So lots of them are big, but then you form a hydrogen bond and it goes away. Then you form a hydrogen bond and it goes away. And in general, the lifetime of a hydrogen bond, wouldn't you know it, is about 300 femtoseconds. And so that's the lifetime. You excite the high energy vibration on the molecule, that keeps going, but the molecule rotates and breaks the hydrogen bond, so it's no longer talking to the lattice. It's vibrating, but it's not hitting anything. So that is our model for why we see this coupling, but why it has the lifetime that it has. And so we think there are opportunities here to design molecules that would talk to the lattice and promote particular optoelectronic properties. So another proof that this is true is we actually took this molecule, and in our theoretical simulations, we induced the vibration. You see, we moved the carbon to the side, so then it's going to oscillate back and forth. And then we saw the band gap oscillates. And if you Fourier transform this, wouldn't you know the frequency of 1700 wave numbers is where the band gap oscillations happen. So this is showing that in our simulations, the vibration of the molecule is directly talking to the band gap. Okay, so I'll tell you about a couple of more recent materials design studies that directly build off of what I just told you. What I was saying is that we have lots of ionic motion in these materials. They're soft, the ions move very far, they're anharmonic, we said all of these things. And that was good for photovoltaics. It kept the electron and hole apart. It turns out that's bad for LEDs. So my other half of my friends want to use these hybrid perovskites for LEDs. for the exact reverse process. Don't shine light on them and get electricity. Put electricity into them and get light, okay? And it's actually a wonderful idea. And hybrid perovskites are setting records for the most efficient LEDs. So that's another great application space for these materials. Okay, so now all these vibrations that keep the electron and hole apart from each other, that's bad news, you see? So we did materials design in concert with my wonderful friend Tae-Woo Lee from the Seoul National University. And I'll tell you about our understanding of what's happening. Okay. So I'm just sort of reminding you here, we have lots of vibrations, and that's going to be a problem. Okay, so of course, as a theorist, we mostly study the active material, but my experimental friends know how to build these stacks and take an anode and a hole transporting layer and the perovskites and an electron transporting layer. And okay, so here is one of our earlier ideas. Oh my gosh, this was so surprising that it worked, but it'll give you this idea of materials design building on our understanding. Okay, so I showed you this idea of 4-mamidinium. We just saw the Viper study. So 4-mamidinium lead bromide is a very nice crystal, but look at this one. This one is called guanidinium. Can you see it has 3 nitrogens? This guy is just too big to fit in here, okay? It will not fit. So my friends made nanoparticles with a certain fraction of 4-mamidinium and a certain fraction of guanidinium. So the guanidinium went to the surface sites, and that determined the size of the nanoparticle, that it needed to make nanoparticles small enough so there were enough surface sites for all the guanidinium. So by picking the ratio of these two things, that made very monodispersed nanoparticles. So that was one breakthrough. But the second thing is having the guanidinium at the surface, the extra nitrogen held the last bromine in place. It made an additional hydrogen bond that you wouldn't otherwise have, and it stabilized the surface and made fewer defects at the surface. So this actually boosted LED efficiency, because if you have defects, those are places an electron can lose energy without actually radiating light, and that's bad. Okay, so the next thing they did is they included these large molecular additives. Okay, so for theorists like me, these are really intimidating. You see how big these are? That means big calculation, and maybe we won't understand anything. But they actually incorporated these molecules and found that it increased the efficiency, so we thought we'd like to look at this. So here is our idea. How do we think about these molecules? They have multiple attachment points. That's what I really should have showed you. Here, remember we think that an amine can be a group that kind of hydrogen bonds to the perovskite surface. This has 6 different N groups. This one has 3 phosphonium groups, and this one has 3 nitrogens as well. So they're connecting to the surface in multiple places, okay? So my analogy is, if you suddenly have a small earthquake tremor, what do? You try to grab different points on your desk to stabilize things so nothing falls off, you see? And so no one ligand attachment point will stabilize anything. But if one molecule is grabbing here and there and somewhere else, it starts to stabilize the surface as a whole. And it can suppress some of these low frequency vibrations that are causing so much trouble by scattering the electron and hole. You see? So we were actually able to prove this with first principles calculations. That first we showed if you take this material and then you put these molecules on and you say how stiff is the material. We calculate the energy versus deformation. If you don't have these molecules, here is the parabola of energy versus strain, but all of the molecules stiffen it. Can you see that? So back to the mechanics idea. From a mechanical point of view, it's literally making it stiffer by having a multi-point ligand. So that's pretty neat. But what we did that's even more direct, we got one of my friends, Omer Yaffa, involved, who is great at taking Raman spectra. I'm getting there. Here. So we calculated the Raman spectrum without any additives, and the peak is here, like at 40. But then if you add any of these additives, the peak shifts. It's not a huge shift, but it goes to like 60 or 55. And so you're taking the low frequency modes and you're hardening them. So it will somewhat have smaller amplitude, higher frequency motion. This moves you in the direction of less electron hole scattering, less keeping them apart, faster recombination, higher efficiency. And I don't know if I have it in here, but the point is my friend Omer and his group took Raman spectra of these actual materials. And wouldn't you know it, the Raman frequency experimentally does shift upward. So that was a prediction that we made that he was able to show. Maybe this is the, here, this is the experiment. Here, so this is the one without the stiffener, and then you can see the blue peak, it again shifts. This is actual experimental data. Okay. So I think that's really neat that we've developed a new principle. I would say that a multipod, a multi-binding site ligand, can stabilize the surface of these soft materials and lead to greater LED efficiency. This is something that we'd like to say, well, but what would be the best multipod? Those were just molecules that they had lying around. They have other purposes in optoelectronics. So we think there's a lot that can be done in designing these kinds of things. Okay. All right, so again, using materials design, now instead of ligands, we're talking about molecules that chaperone growth of the phase that we want. Okay, so I spent, 45 minutes talking about the perovskite phase. Okay, well, the material that some of my friends want to make is 4-memadinium lead iodide. But look at the phase diagram. It likes to make these other phases. And unfortunately, there's this phase, do you see it's not even corner sharing octahedra? Because they're not connected, it's not going to be good for electron and hole transport. It's not a good photovoltaic material. It's made of exactly the same stuff, but it seems to be favored. Okay, so that's very sad. But we don't give up so easily. My friends noted that if you grow 4-memadinium lead iodide in the presence of a phosphonic acid, then you can make the cubic perovskite. Here, this is like an X-ray diffraction, that if you have the phosphonic acid, you get the cubic phase. If you don't have it, you get this other delta phase. Okay, and so a phosphonic acid just means a phosphorus with this, you see double bond O and 2 hydroxyls. So this is the phosphonic acid group. And so these all have abbreviations. This is ethyl phosphonic acid, propyl phosphonic acid, and so on. Okay, so we needed to answer the question, why is this delta phase being suppressed by just having phosphonic acid around, and only certain phosphonic acid actually work? Oh, I should have said that. They had these 4 candidates. Only this one is good. To see the one in the green box. So why did these other very similar ones not work? Okay, and so we were able to answer all this, and it comes down to the idea that the crystal would like to bind to these phosphonates. You see, the crystal as it grows has all these sort of dangling bond sites, so the phosphonates would bond to it, and it stabilizes them. But actually, the delta phase has a lot of internal bonding. It doesn't really care about the molecules that much. So the point is the delta phase is equally happy either way, but the molecules really favor the alpha phase. And so that leads to this kind of a graph, that if you have the molecules, the alpha phase can be more stable. But if you go thick enough, actually the bulk of the delta phase is favored, but it's too late. Once you've nucleated the good phase, it'll keep on growing even when you go past this crossover point. And so it's really getting it started in the right way with the phosphonates saying, don't worry about your dangling bonds, we got you. And so this is another aspect of materials design based on understanding the physical principles. And so I think I'm out of time. Does that sound about right, Al? Well, I'm just thinking if there's, I'm looking at what I still have to say. I mean, it turns out it's a little more complicated than this. The actual mechanism is they deposit the phosphonic acid. This is our model. And so then the crystal starts to grow. But then these phosphonic acids get out of the way and diffuse to the top surface because they want to bond there too. And so you need to have enough phosphonic acid to kind of cap the top as well as the bottom. And so these phosphonic acids keep kind of migrating from the bottom up to the top to keep the material happy. Okay, so yeah. Okay, so the last story I will tell you comes out of a lovely collaborative center that we have. The host, the lead institution is the University of Washington. And so this was a collaboration with Gordana Dukovic and David Ginger through the NSF Center for Integration of Modern Optoelectronic Materials on Demand. And so this was a way of moving forward our ligand design even one step further, as I'm saying, to make more efficient light-emitting halide perovskites. So I think I already mentioned that these halide perovskites are turning out to be wonderful LED materials, and especially for green light-emitting applications. That seems to be perhaps the sweet spot for cesium lead bromide and related materials. But they have a problem that is referred to as blinking, where they will be emissive dots for a while, and then the dot will not emit for some time, and then it'll go back to emitting. And it's thought that this relates to defect trapping, that if you have a trapped hole and a free electron, then that electron gets involved with other carriers and facilitates them losing their energy non-radiatively. And so the idea is if we can remove the defects, we're pretty sure we can reduce the blinking. And so the experimental observation is that using lecithin, capping the quantum dots leads to much less blinking. Okay, so this is a histogram of how many of them are non-blinking at any given time. And the lecithin shows that almost 20% of them are not blinking. Whereas if you have these capping ligands, oleolamine and oleic acid, then you only get like 2% non-blinking. Okay, and so here you can see we have like carboxylic acid, and here we have an amine. And so these become sort of like a carboxylate and an amino, so a negative and a positive. But instead, the lecithin has the negative and the positive on the same molecule. So the main difference is whether you have two ligands, each of which has one charge, and one ligand that is both. And so I'll come to the main reason we think there's a difference here. And that is when you bind the lecithin to the surface, it binds more strongly than the oleolamine or the oleic acid, that those bind pretty well, but not too bad. But then when you include the effect of solvent, you see the lecithin or these oleolamine and oleic acid, they could just go off and join the solvent. And it turns out solvating the two separate molecules is much more stabilizing than it is stabilizing for the lecithin. So this is the binding of lecithin in the presence of solvent. And this is the binding of these other guys. It's too weak. It's not really fully covering all the sites. It's not passivating all the defects. And that's why we think lecithin offers enhanced resistance to blinking. Okay, so I think every one of my projects in some way involved understanding, analyzing, or dealing with the large mechanical deformations that could be an opportunity or could be a problem in the hybrid and halide perovskites. But how we handle those mechanical issues is through chemistry and through harvesting of favorable optoelectronics. And with the moment I have left, I'd like to put up a list of my wonderful collaborators. Each of the projects I told you about had a vibrant experimental component, and it's a great joy to be able to work alongside such talented leaders in the field. And these are some of the folks from my group who contributed to the work you see here today. And here's a recent photo of us. And I would like to thank the support of the Department of Energy, of the IMOD Center through the National Science Foundation, the Navy, and then we did calculations at the NERSC Supercomputer Center and the DoD High Performance Computing Modernization Office. And I thank you for your attention, and I look forward to taking your questions.
For questions, I have to use the microphone, so I'll be passing the microphone for the recording. So, yes.
Thank you very much for this really interesting talk. I was intrigued by the effect of the atomic vibrations on the electronic structure and how that really controls the efficiency of solar applications or LEDs. But then again, we know that atomic vibrations depend very much on the absolute temperature. So does what you have shown us imply that if I had a solar cell, I would have to carefully control its temperature, which I imagine could be a hard thing to do in changing conditions? And conversely, if I had an LED that's operating on this principle, would I have to control its temperature so that it produces a constant output?
That's a wonderful question, thinking about the role of temperature in the electron-phonon coupling that I discussed here today. So what I want to say is these materials are so soft, the ions go so far that the energy mixes with other modes almost right away. What I like to say is that the vibrational lifetime, the amount of time that a vibration keeps its energy before it goes somewhere else, is shorter than one vibrational period. So it goes out, before it comes back, it's something else, and it's something else, and it's something else. So the energy is wandering all over. That we call the anharmonic limit, okay? So you're not going to be able to control that very easily with temperature. So remember, that effect is helping you in the photovoltaic case. That is hurting you in the LED case. But we're going to settle that down with chemistry. We're not going to be able to settle that down with temperature. So we either alloy the material, or we put something adjacent to it that settles it down, and all of that can lead in the right direction.
Okay, thank you.
Beautiful talk. I was impressed by how you get mileage out of the molecular dynamics and combine all of these phonons and are able to do this thing. That's a feat. My question is to do with, you mentioned basically for the solar cell applications, you want to keep the electrons and holes apart, and you say these things help us. But at the same time, this lifetime, that's just the electron-hole recombination time, but the individual electrons and holes have their own scattering times as they move, right?
Yes.
And I was wondering if you have such a disordered structure because it's all the time moving back and forth, that must lead to like restricting mobility of the electrons, how far they can go in the hole. They don't recombine, but their motion must be hindered. And if it's so strongly disordered, you could even get localization phenomena, right? Have you worried or seen any indications that you would get localization effects?
Yes. What I'm describing with the electron goes here and the hole goes there is transient localization. They're localized, now they're localized somewhere else, now they're localized somewhere else, but they can scatter to the exit. If you have a hole transporting layer and an electron transporting layer that are close enough, they will get there. You see, because they have a long lifetime, even if they walk slowly, drift slowly, they will still get there. And so that's why you have high efficiency, even though the mobility is known to be low. But it is because of the long carrier lifetime that they are effective. And the material is so strongly absorbing. A fairly thin layer of hybrid perovskite is good enough to get all the sunlight, so you don't need to go so far to get to the electrodes. Remember, silicon is an indirect band gap, so you need thicker. This one you can have much thinner. Yeah.
Andrew, I enjoyed the talk. I was wondering interesting ways that you were probing the mechanical aspects of these nonlinear elastic materials early in the talk.
Yes.
And so you showed these interesting experiments where you used a rubber substrate to cause wrinkling, which lets you back out the modulus. So my wondering is, is the modulus pretty much single valued, or does the wrinkle or wrinkles occur in the low modulus material, and you really have a distribution of moduli that could be both temperature as well as strain rate affected that would be relevant for an application?
Yes. The modulus is not single valued. So at the very least, you would need to have out of plane and in plane moduli. And so the indentation mostly measures the out of plane, and the wrinkling mostly measures in plane, although there's some, bending effect that is mixing those up. But for the rest of the modeling, I was then focusing on the out of plane, because I think the unloading experiments of the out of plane are the cleanest set of data, because the wrinkling is very sensitive to layers sliding against each other, not the intrinsic compression and stretching of the layer. And so that would be an interesting further study, but we didn't follow up on that. So the wrinkling is reported, but the modeling that we did was geared toward the Oliver Farr indentation part, which we thought was it was complicated enough, but that was the cleanest subset of the data. Yeah.
I have a question. So in the early parts, you were putting different size molecules. You were talking about the size effects, and certain molecules go and certain molecules don't go. And then later on, you talked about the stabilization using multi-pod molecules, how they respond to different stresses. And I was wondering how much there is an effect of the possible design parameters, such as designing different twisting and tilting bonds or smaller backbones, maybe small size molecules, polymers to use in these structures to improve some of these or modify the compliance of these systems.
I think the field is still wide open. People have tried many things, but it's mostly based on experimenter insight. And so the idea of doing broad molecular database studies, theory and experiment with rapid experimentation in parallel, that's taking off now. And so I'm part of one of those teams. I'm sure there are many groups that are currently trying that right now. But the idea of having molecules that are more tilted, yeah, we said a little bit about that. That wasn't something we designed in. But in the future, designing in the way the van der Waals and the other interactions lead to the material stacking and compliance will be very important. I think we will continue to be surprised because molecular variety is almost infinite. But we think we've discovered some of the main principles that we know we're going to look for, and we think we can improve the material properties based on that. But then we probably will be surprised again as we develop some of the leading candidates and we see how much we're able to improve the properties.
One last student question, right?
So in your slide 22, you showed that Raman peak broadening that you achieve from molecular dynamics calculation. So we usually know that this Raman peak broadening is associated with electron phonon or phonon-phonon interactions in solid. So how does your molecular dynamic modeling achieve this kind of science?
Yes, thank you. In our case, it's almost all phonon-phonon interaction. You are right. A lot of times people say, find the phonon frequencies, then include corrections as a perturbation. What we are showing is that you can do molecular dynamics, and so every phonon that vibrates, it might be in the presence of one other phonon, it might be in the presence of 5 other phonons, or 3n other phonons. You see, the whole system is thermally oscillating all at the same time. So you just get a variety of interactions to all orders. So don't think of it as just a quadratic treatment or cubic or quartic. We include the phonon couplings to all orders. That's one of the benefits of doing it the molecular dynamics way. Sometimes doing a sum order by order can give you some insight. But here I think we're outside of the perturbative limit. So I actually like this treatment a lot. So that's how we're including phonon-phonon by the vibrations are all happening at the same time, so their interactions are literally included in the polarizability, which leads to the full Raman spectrum. Yeah, thank you.
All right, if there are no more questions, let's thank our speaker one more time.
Thank you.
Before you leave, I would like to also thank Professor Rappe for this first of the 3 lectures. And as a part of the One Horn lecture series, and as one of the leaders in the field, we would like also to share the plaque with him.
Oh, okay.
Thank you.
Thank you. Wow. Thank you, everyone. That's really amazing. Thank you.